Okay, so here is another sample problem. So let us familiar more about how to calculate the surface integral. Okay, for some simple cases. Okay, so here it says, okay, so here is non-uniform electric field. Okay, so this one is uniform, so it is quite straightforward. Okay, so this one, a non-uniform electric field given by E equals this expression, P is the Gaussian cube. Okay, so this is also a Gaussian surface or closed surface, which is a cube. Okay, so of course, for a cube, there are 6 square sides. Okay. Okay, so as shown in the figure, so E is blah, blah, blah. Okay, what is the electric flux through the Y phase? Okay, so there will be several questions. Okay, so the first question is asking you to calculate the electric flux for the Y phase. Okay, actually this one. Okay, so so for this phase, dA is actually pointing to the right side. Okay, actually pointing to the right side. Or you can write it as dA times actually the positive x-axis. Okay, so because we have here x, y, and z. Okay, so this is positive x-axis pointing to the right side. So we use so we use I hat here. Okay, I hat here to represent the unit vector in x-axis. Unit vector in x-axis. Okay, so here we can calculate E dot dA for the right surface. Okay, we use a small r to represent the right. Okay, the right. Okay, so actually this one is not a lower upper bound. So a student just asked me, okay, oh, how come it only have a letter at the bottom? Okay, it just refer to something. Okay, so let's say, okay, if I refer this to the right face, okay, I just write an R, or if you like capital R is also okay. So just refer to, but of course you need to define. Okay, of course I define it by my mouth. Okay, just tell you that, okay, this R refer to the right face. Okay, and it is straightforward because it is the sample problem asking you the net flux or the total flux for the right face. Okay, so So of course we have E dot dA. Okay, here will be like 3x I hat plus 4j hat. Okay, 4j hat. Okay, so just replacing E by this expression and then dotted with dA and then I hat. Okay, so here dA already become a scalar. Yeah, the only vector. Okay, so the vector here is this one. Okay, so this one dotted with this one. Okay, so so this is a simple result for the IJK Okay, let me add a page here. So for the let me see, I dot I will be 1, J dot J will also be 1, and then K dot K is also 1. Okay, so I is the unit vector for x-axis, and then J is the unit vector in y-axis, K is the unit vector in z-axis. Okay, so any of the two combination like I dot J will be 0. J dot I is also 0, and then I dot K is 0, K dot I is also 0, and then J dot K is 0, K dot J is also 0. Okay, so only the unit vector dotted with itself dotted with itself will be 1, and then any of the two different unit vector dotted will be 0. Okay, so it's just this easy case. So here for the first one, okay, we have 3x I hat dotted with this one will be I dot I will be 1. So we have integration of 3x. And then for the second one, and then of course we have a dA here. Okay, for the second one, we have a j hat dot I hat will be 0. Okay, so yeah, this is great, like this. Okay, so for the right face, we can see that for the right face, x is all the way 3 to be 3. Okay, so for this plane, this is x to be 3, x to be 3. So this is nothing but 3 times 3 dA, okay, which is 9, okay, which is 9. So this is again integrating a constant, okay, integrating a constant. So which is like 9 times the area of this surface is like this is 2, this is 2, this is also 2. Okay, so the area here will be 2 times 2 will be 4 meter square, right? So 9 times 4 will be 36. Okay, just now I forgot to mention is that the SI unit. The SI unit will be like this is N over C, and then this is M square. Okay, this is area should be M square. Okay, M square. This one goes to here, and then E field will be partly go to here and also here. Okay, so the SI unit for the total thrust or net thrust will be N M square over C. Okay, so here, N M square over C. Okay, so this is the answer. Okay, so this is the first one, and then we have the second one. The second one asks you the left face. Okay, the left face is here. Left face is here. Okay, so similarly, we have a dA pointing to the left side, okay, actually opposite to the previous case. Yeah, so this is actually dA times also I hat, but with a negative sign, yeah, because it is a negative x-axis, right? So in this case, integration of E dot dA for the left, okay, for the left surface, which will be like integration of 3x I hat plus 4j hat dotted with negative dA I hat. Okay, so similarly, I hat dot I hat will be 1, okay, but with a negative sign, so we have a, will be negative integration of 3x dA, okay, for the first term. And for the second term, j hat dot I hat will be 0, okay, so it will be like this, okay, for the left surface. Okay, but for this one, x is 1, okay, x is 1 instead of 3, okay, so here it should be integration of 3 times 1, okay, rather than 3 times 3, okay, and then dA. Okay, so 3 times 1 is 3. Okay, so similarly, negative 3 times 4. Okay, also the area of this of the left surface is also 4 meter square. So this is a negative 12 N M square over C. Like this. Okay. Yeah. Okay. So for the third case, okay, the top face is here. The top face is here. So the dA is pointing upward. So it's a dA, and then this is a positive y direction. So it is j hat for the positive y axis. So similarly, E dot dA, and then for the top surface T will be integration of 3x I hat plus j 4j hat, and then dotted with dA j hat like this. Okay, so this time I hat dot j hat will be 0. Okay, so first term is 0, and then the second term integration of 4, and then j hat dot j hat will be 1. Okay, so j hat dot j hat will be 1. So dA, and then for the top surface like this. Okay, so this time it is already a constant. It doesn't relate to x anymore. So in this case, it is 4 times 4. Okay, also the A is 4 meters squared. So this is 16 nm squared over c. Okay, so so far any questions? Okay, so from these two sample problems, we have learned some simple case, okay, for how to calculate the flux, okay, the electric flux. Yeah, just for some simple case. Okay, so here, so we suppose you will be able to find, okay, what is the flux. So here, it just tells you that, okay, so the Gauss law, okay, so after knowing how what is the electric flux, we can really talk about the Gauss law. So actually it says the Gauss law relates the net flux of an electric field through a closed surface. Okay, so closed surface is very important, or Gaussian surface is very important to the net charge Q enclosed that is enclosed by that surface. It tells us that, okay, epsilon naught, okay, so the permittivity, okay, we define in chapter 21, so 8.85 times 10 to negative 12, and then this is the net flux, okay, the net flux. The epsilon naught times the net flux will be the Q enclosed, okay, so the Q enclosed. Okay, so it's just like the F over MA, it's just like a multiplication, so yeah, we cannot do too much. So here we just try to write it as integration. Okay, so to replace this phi as the definition of the net flux. Okay, so as the closed surface integral. Okay, the closed surface integral. Okay, so which will be nothing but epsilon naught times this surface integral, closed surface integral of E dot dA equals Q enclosed. Okay, so looks quite horrible. Just like F equals MA, F equals MA, F equals MA can be like can be usable by high school student. Okay, even if you haven't learned the calculus, but actually in bachelor study, probably if you would like to use it, it will be better to be written as F equals M second derivative of x with respect to t, okay, something like this. Yeah, with this expression, you'll be able to write some differential equation. So it will be more useful, just as this case, okay, for this one, it's just like multiplication, just like F equals MA, but here we try to replace it as a surface integral. Okay, so let's go back. How do we understand it? How do we understand it? So here we have several cases to consider. So first of all, let's consider this S1. Okay, of course, in this big figure, there are two charge. Okay, one is the positive charge on the top part, and then another negative charge with the same amount at the bottom part. Okay, so we consider this is plus Q, this is negative Q with the same amount but opposite sign. Okay, so first of all we try to consider this S1. Okay, on the top one. Okay, so this S1, this S1 will be like this. Of course, this is a curvature. Okay, it doesn't really matter what the shape it is. Okay, we just assume this is a closed surface. Okay, of course in 3D. Okay, so this S1 encloses this positive charge, which means that this negative charge is outside. It's outside of the S1. Okay, outside of S1. Okay, so only the positive Q is enclosed by S1. Okay, so here it says two charges equal in magnitude but opposite in size, and the field lines that represent their net electric field for Gaussian surface are shown in cross section. So here it says, phi is phi 1. Okay, phi 1 referring to S1. Okay, is positive. What it means is that as much as for the S1, okay, it encloses a positive charge, which means that Q enclosed 1 is positive, and then epsilon is of course positive. So which means that this phi 1 is positive. So we consider it like this. Okay, so for epsilon naught, phi 1 is Q enclosed 1. Okay, so for this one is nothing but plus Q here. Okay, plus Q here. So which is larger than 0, and then this one is also larger than 0. So phi 1 is larger than 0. We don't need to care about what is the magnitude. We don't care about it here. We only learn how to So the size. Okay, the polarity of the flux is enough for this case. Okay, so next, phi 2. Okay, phi 2 of course referring to S2. Okay, so S2 is at the bottom part. Okay, here S2 is here, so referring to this part, to this part. Okay, so this part. Okay, so which means that S2 only encloses the negative Q, positive Q is outside of it. Okay, so here the second case is like epsilon naught times phi 2 is Q enclosed 2, okay, which is negative Q, which is less than 0. So this one less than 0, this is positive. So phi 2 is also negative. Phi 2 is also negative. So as you can see, okay, so as you can see for example S1, okay, you can see, for example, all the E field line are going out, are all going out, and then for example, let's say this one, okay, dA is somehow pointing that way, okay, and then this is the E field, okay, so E dot dA, even though it is not 0 degree, and this is an acute angle, okay, less than 90 degree cosine, and acute angle should be positive. So we can see, okay, so this d phi is positive, this d phi is also positive, so on and so forth, and then adding all these positives together. Okay, so by the definition of the net flux, you also know that, okay, this is positive, but yeah, actually this is also mentioned in the or implied by the Gauss law. And here for S2, Yeah, for example, okay, this one, dA points to this side, okay, but E field is, yeah, it's like this. Okay, so theta is like larger than 90 degree, less than 180 degree. So cosine of this theta is negative. Okay, so all the d phi correspond to S2 will be like negative. So it's like adding many negative number together. So it turns out to be phi 2 to be negative. Okay, so for the third case, S3 is here. S3 is here. Okay, so clearly S3 encloses nothing. Okay, so which means positive Q, negative Q are all outside of this S3. So for this case, epsilon naught phi 3 equals Q enclosed 3, which is 0. Okay, nothing is enclosed. No charge is enclosed. So this positive Q, negative Q are outside of this Gaussian surface. So both neither of them counts. Okay, neither of them counts towards the Q enclosed. So equal to 0. So which means that this is positive. So which means phi 3 must be 0. Phi 3 must be 0. Okay, so for this one, you can see that, okay, so part of it will be positive, part of it will be negative. For example, okay, this part, okay, this is dA. Okay, so this side tends to be positive d phi. And then for this part tends to be negative, tends to be negative. So, but the Gauss law tells you that all these positive and negative d phi will perfectly cancel each other. Okay, turns out to be phi 3 to be 0. Okay, so this is what Gauss law tells you. And then for the fourth case, okay, so the big egg, okay, so this one, a big oval. So S4 is this one, okay, enclose both positive and negative Q. So which means that epsilon naught phi 4 equals Q enclosed 4 will be plus Q minus Q, which is also 0. Okay, so which means that this is 0 and then this is positive. So phi 4 is also 0. So similar to this one, okay, you can also see that, okay, so this part tends to be positive. This part tends to be positive. This part tends to be negative. So adding all of them, the d phi together, okay, Gauss also tells you that the sum of all the d phi will be phi 4 will be 0. Okay. So any questions? Okay, so this is so the difficult part here. So we need to use the surface integral. Okay, the surface integral. But if you can accept the surface integral, then applying the Gauss law will make the computation easier. Okay, rather than doing the integration by yourself. Okay, because applying the Gauss law for some symmetric structure, then it will be like integrating constant for some specific surface, and then it will be like integrating a constant will be like a multiplication. Okay. So here it says the Gauss law actually compatible to the Coulomb's law. Okay, compatible to Coulomb's law, or actually they are equivalent to each other for this case. Okay, so what it means is that, suppose we have a positive charge here, okay, and then we define a Gaussian surface, which is a sphere, okay. So this charge Q is at the center of the Gaussian surface of this sphere. Okay, so in this case, we try to apply the Gauss law for this Gaussian surface. So which means that we have a epsilon naught integration of E dot dA equals Q enclosed. So for the left part and the right part, which is the Gauss law itself. And then for this specific case, as much as we only have a single charge and then this is a sphere, so for every small element, okay, let's say here, dA actually points to this direction, and also E field also points to the same direction because it is totally symmetry, okay, totally symmetry. And based on what we know, okay, so as much as this is a positive charge, all the E field start from the charge and then pointing outwards. So which means that E field and dA at any point, okay, at any point will be like parallel to each other. Okay, so this is E field, okay, E field dA, okay. So all the E field dA points to the same direction, which means that this is like epsilon naught. Maybe I change it back to the blue color. This is like epsilon naught integration E times dA cosine of 0 degree. Okay, cosine of 0 degree is nothing but 1, so it is like E times dA. Okay, I just ignore the dot here. So E times dA. Okay, but you know that dA is is a single variable, or the integration. Okay. There. Okay, so it will comes like this. Okay, based on this structure, we can go from the left one to the middle one. Okay, so and then also we know that E field should be a constant over the whole surface, because the distance between every element to the center should be a constant distance. Okay, so which means that integrating a constant, which can be like integrating E dot dA will be like E times dA will be like E integration of dA, which is something like integration of 4 dx is actually 4 times integration of dx from 0 to 3. Okay, so they are all equivalent. Yeah, like this. So so we just put this in the front, and then so for this one, which is nothing but the surface area of the sphere. So I think in high school mathematics, so it already tells you that, okay, surface area of a sphere will be 4 pi r squared. 4 pi r squared. So we just plug in 4 pi r squared to here. So epsilon naught E 4 pi r squared is Q enclosed. So we try to move this part and this part to the right side. So we have a 4 pi epsilon naught here, and then r squared go to here, and then Q enclosed is here. So this is nothing but the Coulomb's force, or F equals 1 over 4 pi epsilon naught Q1 Q2 over r squared. Of course, this one is the Coulomb's force, but this one is based on the Coulomb's force with the definition of E field. So with the definition of E field, F equals E equals F over Q0. Okay, so with these two we can have this one. So actually this one is also compatible to the Coulomb's force. And then based on the same situation, and then we can use the Gauss law to really derive the same equation, which means that the Gauss law and Coulomb's law, or the Gauss law and Coulomb's law, are actually compatible to each other or equivalent to each other. Yeah, as I mentioned, both of them are law, so we cannot prove it. So if you want to disprove it, which means that you need to find some counterexample. But of course, since it was invented, okay, I think it's around 200 years ago. So so yeah, we couldn't find any counterexample. So which means that okay, it should be correct. Okay, so here we have another sample problem. So it says in cross section, okay, in cross section, plastic spherical shell. Okay, so plastic means it is non-conductor. So which means the charge are not free to move, no free electrons on the non-conductor. Okay, a sphere shell with uniform charge Q equals -16 e, and radius R equals 10 centimeter. Particle with charge Q equals 5e. Okay, so this is the 5e. Q equals 5e, and this is -16e. At the center, okay, what is the electric field, magnitude, and direction at the point P1? Okay, P1 is actually inside the sphere. At the radius distance, R1 equals 6 centimeter. Okay, so okay, so here we try to assume the Gaussian surface is actually here. Okay, it is a sphere with the radius R1. Okay, so this is R1. So for this one, we only draw the Gaussian surface and also the Q. Okay, and then the outer surface is according to Gauss law, we don't really care about the outer the things outside. Okay, and then here we try to apply the Gauss law for this Gaussian surface. So epsilon naught integration of E dot dA equals Q enclosed question A. Okay. So according to similar things to here, we try to skip through. Okay, so this is this will be E integration of dA equals this is small q, which is 5e plus 5e. Okay, similarly, epsilon naught E times 4 pi R square will be equals 5e. So in this case, E will be 4 pi epsilon naught, 1 over 4 pi epsilon naught, and then 5e over R square. Here, actually, R can be between 0 and R1, okay, or 0 and capital R, okay. So here, this one is actually correct. This one is actually correct if R is smaller or equal to, let's say smaller than capital R and or larger than 0. Okay, so for this, okay, for this range, okay, R should be correct. Yeah, because yeah, we can just enlarge or make the Gaussian surface smaller. Okay, make this sphere smaller or bigger. Yeah, it still encloses this small cube. Okay, so it still be correct. Yeah, but actually R1 is only one variable between 0 and capital R. Okay, finally we can of course plug in R to be R1. Okay, so that we will know the E field at the point P1. But this is just a general expression. Okay, so this is the expression, and then we can actually for E of R equals R1, okay, which will be 8.99 times 10 to the 9th power, and then 5 times 1.6 times 10 to negative 19 over R to be R1 will be 6 centimeter. 6 centimeter is 0.06 meter, and then square. So this will be 2 micronewton per coulomb, okay? Or you can say 2 times 10 to negative 6 Newton per coulomb. In the quiz or exam, you can either answer one of them is enough. You don't need to answer both. But as I mentioned last time, okay, in the slides of chapter 22, you must remember all the scientific prefix. Okay, don't ask me what is the definition of mu, what is the definition of n, what is the definition of p, what is the definition of f. Okay, so I won't tell you the value of those scientific prefix during the quiz or exam. Yeah, you need to memorize them, as I have summarized in the slides of the chapter 22. Okay, so this is for question A, and then go to question B. Question B is in cross section. So ask you the E field at point P2. Okay, so the top two lines are exactly the same. So here it just asks you the P2. Okay, the P2. So here we just assume R is greater than or equal to capital R is enough. So similarly, here is the Gaussian surface where R is larger than capital R. Then we can draw it like this. So epsilon naught integration of E dot dA for this Gaussian surface for the Q enclosed B part will be like Q plus capital Q. Okay, because this Gaussian surface, if R is greater than capital R, we enclose both Q and capital Q. So Q plus capital Q. So on the left part, which is actually the same epsilon naught E times 4 pi R square. Okay, but pay attention. Okay, usually we do it like this in this course. Okay, because it is spherically symmetric. 球面的对称 okay, spherically symmetric. So this one, okay, will goes to this line. With the steps like this, okay. But if it is not symmetry, okay, then you need to go into the steps one by one to see whether it will go to here. Okay, so it is actually 5e minus 16e, okay, according to this one and this one, okay, which is a negative 11e. So e will be like 1 over 4 pi epsilon naught times negative 11e over R squared. Okay, so if E is E for R to be R2 will be 8.99 times 10 to the ninth times negative 11, and then 1.6 times 10 to negative 19 over, this is 12 centimeters, 0.12 squared. So which is negative 1.1 micronewton per coulomb. Okay, so here it means that if you know the Gauss law, then yeah, so yeah, it can simplify the computation, and yeah, and it is quite easy for you to determine, okay, what we need to count for. Okay, as much as you need to make the correct assumption for the Gauss surface. Actually, for every single case, you can define arbitrary Gaussian surface, but most of the case the Gauss law won't work. Okay, as much as the Gaussian surface fits that cases, okay, then when you apply the Gauss law, that okay, you can get some meaningful conclusion. And for example, this kind of symmetry case, then it is straightforward to define the Gaussian surface to be a sphere, yeah, with the center at this kind of at the charge. Okay, so which means that the Gaussian surface will have quite a lot of symmetry. Even though the radius of the Gaussian surface increase or decrease. So yeah, the Gaussian surface will have all the way symmetry if you along the surface. Yeah. Okay.